Okay, so sometimes you may want to represent the whole of this Nyama thing here with a letter M and come and substitute that. So your sigma H looks more friendly and not frightening. So you have M dV. But then still, you have to go and write this somewhere and solve it and now get the M. So why worry your head? You still have the same trouble. So stress distribution in a rectangular pillar 2, the average stress for a rectangular pillar 2, you are going to have this. This is the area. This is the length of the pillar, the width of the gallery, width of the pillar, and width of the gallery. Then times this. You realize in the square, this was WP to the power 2 by this time around. So your average stress, when you compute them, you come up with this formula. So if it is a rectangular pillar, this is what you should expect to have. So let's solve this question. It says that find the institute stresses at A and B, assuming the overburden is sandstone whose weight density is this pounds per feet per cubic feet, or PCF, with Poisson ratio of 0.3. And it says that figure 35 depicts the vertical stress dV on axis due to conical loading. So you have a plot of land or a piece of land where there is a coal seam which you are aiming at mining. And you realize that at a certain point called A, the whole land is leveled. So it's the same. But when you go to the point B, there's some kind of a mountain or a hill, which is going to add to the weight that if there is a pillar here at the point B, the pillar there will be different, will bear a different amount of load. So we want to compute that. So the average stress at the point A is this. This value was given as times, because it is not times the feet, which is 200 feet, and we want to divide by this unit in order to get our PSI. So once we get this value, the corresponding horizontal stress is also going to be the Poisson ratio, which is this expression, times the 240 PSI. And then we get this. And that becomes the stress. If there were to be a pillar at A, that is the amount of pre-stress it is going to bear or carry. Then where the problem is the B. The B, because of the mountain, we have to calculate the stress at the 240. We already know, because they said that from this side to this side is 200 feet, but from the floor to the top of the hill is also another 200. So we already know the first 200, with this is what we want to calculate. And then to go by that one, we first have to calculate A, which is this one. So the mountain will be divided into two like that. So to the left of it is A, to the right of it is A. So we have 2A. And so to find A, what will A be? A will be 100 divided by 2, and that will be 50 feet at each distance. So we are just calculating the distance between the middle of the cone, which is 7 as the mountain here. Then there is a chart which we use to compute 4. If not, you'll be misled to think that there's an approach to this. We don't calculate the 200 as though it were also a whole pillar on its own that is bearing vertical stresses and whatnot. No. So we treat the mountain aspect separately using this chart. So we have to first get the rho over P component of the chart. So we have to calculate this section, and then we know this, isn't it? Which is Z over A. And on the graph, you could see this diagram, this beautiful diagram, depicting if you have a cone, a conical mountain like that, from the middle of the cone, we call it the A and A. And the distance below it is the Z. So the distance below it being the Z, we know, which is 200. And that is what is here. So Z over A, which is this one, you divide how many of, but you know your A is what? 50, because we calculated the A from here, which is this side of the cone, this section. This section of the cone, where the dot is. So we want to know what that A is, and we know that. So we now have our 200, which is the Z below the mountain to the bottom where we are working. And that will be 200 on 50 because we have worked for our A. And that gives us a value called 4. We get this 4. Then we have, once you have gotten your 4, this is the 4. You draw from the 4 to hit the curve. So we will have something like this. So it hits the curve. And then once you have gotten that, you then draw a line to the top. So from the graph, you realize to the top, you want to calculate the value that is here, and that will represent your this over P. And then calculating that, you now have from 0 to 0.1. What will that value be? So I assume that value from what I see from here, I take that value to be 0. It is not in the middle of the graph. So I took it to be 0.025. So I have sigma V over P is equal to 0.025. Then now, do I know P? Do we know P? Yes, we know P. P is the height of the mountain. So you have sigma P V is equal to 0.025 P. Who does not understand this expression? We want to make this the subject. So we have gotten this. So whatever value we were provided with as P, which is the height of the mountain or the cone, you substitute that here and you have 0.025 times 200. And if you do that, what do you have? You have 5 psi, and that is this one. So now we were told that if you wanted to calculate for the sigma V at the point B, it is going to be the 240 psi plus the mountain, the force at the mountain, which is now gotten to be 5 psi, and that will give us 245 psi. Now you know this, so you can use this to, you substitute that here, and then multiply by the components of your Poisson ratio, deformation along the axis, and you get your sigma, the stress on the horizontal, to be this. Any questions? So tributary area concept.
Sorry, Doc.
Hello.
Quick one. I saw at the beginning of this solution that the average vertical, there's a 144-inch square denominator. Where did we get that from?
Okay, so we were given whose unit weight is, because we were given the value in pounds per cubic feet. Okay, so
Okay.
you know we are dealing with this pounds and whatnot, so we want to do a conversion that will help us arrive at the psi, and so it's just a conversion unit. Okay. So that is why we have that there. Any other questions? In the absence of none, we proceed. So consider mining in, hello, is someone? Okay, so consider mining in room and pillar method. So in a room and pillar method, this distribution, we have been able to come across that, so we don't waste our time again. The cross section through a flat line or deposits of uniform thickness being mined using long room and pillar. So this one too is trying to demonstrate if we are using room and pillar mining, as in the usual mining we do, rather than coal to, the expression is still the same.